So I've just implemented Euler 10, and the performance was not where I wanted it to be. And I tried the Sieve of Eratosthenes, which I found on Wikipedia, as a way to compute primes. And it's this little algorithm here. And I implemented it. And here it is. Here's a prime sieve. And it's about 1,000 times faster for computing primes up to 1,000,000. Which may not translate. I don't know if it translates to Euler 10 here, which is all the primes below a particular value. And it's not an iterator that just goes on forever, but I figured we'd try it. So I'm going to start over here so that you can come along for the ride, and then we'll make the iterator and try to finish the problem. So I'm going to check out main. Let me delete that branch I was on. We'll make a new branch. Check out -bhfs.eratosthenes. Okay. So first off, I want to add a little micro benchmark code here. So we're going to say time instant. Let's let now equal instant now. We'll say let sum equal Euler 10. And we will print line the result, sum, and then also the elapsed time. What doesn't it like? Duration cannot be formatted. Okay, fine. Format it for debug. This takes like 26 seconds, right? So in the meantime, I'm also going to start looking over here at the primes file. Let's add some test code while we're at it. Config test. On test. Use superstar. Function test. Test primes. And then we will say, let's say, I don't know, all the primes up to, we're going to want, yeah, let's say all the primes up to 20. So let primes equal primes new dot take while p is less than 20 dot collect. Well, assert equal primes. I guess this took 26 seconds. Fine. Primes. And let's see, what are the primes? Less than 20. 2, 3, 5, 7, 10, 11, 13, 15, 16, 17, 19. Cargo test -- lib. Expected. Yeah. Because it gets passed by reference. Okay, cool. So that looks okay. Just to verify that if this were wrong, that would fail. Okay. So now let's make a function called prime sieve. Prime sieve is going to take, let's say, I want this to be exclusive. This will be an end value. Yeah, in fact, while we're at it, like before we even do any of that, get stash. Let's go back over to main. And yeah. Yeah, also since we last spoke, renamed functions, that's it. Because I had missed one of these test functions. I had to call Euler instead of Euler 10. Renamed those. So I'm on the main branch, and I want in Euler 10, instead of this limit, I think I want this to be end, because there's a convention often that end is excluded, whereas limit doesn't have that conventional name. Let me just make sure that this compiles. Yeah, that's fine. Okay, cool. Let's say rename a variable for a parameter for clarity. Okay, now where are we? Oh yeah, so let's go over to, we still got a value over there. Is that the same value? 142, yeah, that's the same value. Check out our branch. Reset dash hard main, make sure it matches that. Get stash pop supply. Yeah, cool. .rs. In fact, we've done all we're going to do in the main Euler program for now. The only thing we're liable to do with that going forward, well, that's all right, because we're not even going to end up committing those changes. Those are the things that we're using right now to micro benchmark this. We probably ought to set up some kind of a, I probably ought to set up some kind of a benchmarking for each of these so that we can keep an eye on performance if we refactor the code. But yeah, let's call this end again, just to show that it's excluded. This will be a, is it a U sign? No, this is going to be a U64. Returns vec bool, a vector in which vector mapping indexes to false for non-prime numbers, mapping each index to false for prime. A vector of, yeah, you know what, actually let's just call this n. It'll be a count. We'll make this a usize vector mapping each of its indexes to false if they are true if they are prime and false otherwise. Note that indexes begin at 0. This means that if you want to know whether n is prime, you should call prime sieve n plus 1. Cool. So let's make our vector. This will be basically within the implementation. It starts off true if it may be prime, and then you take each prime number as you find it, and you mark off anything it divides, so you know that they're composite. This will be vec, which will maybe make more sense in a second. It's going to be n values, and they're all going to be true, because as of right now, they all may be prime. That's what we're going to end up returning. Let's watch that. Watch test it. Expected use size found bool. Oh yeah, other way around. So they're all going to be true. Cool. Dead code. Let's add. It should be pub, because we'll need to call it from the other crate, from Euler 10. And we'll say, actually, will we need to call it from Euler 10? No, probably not, because Euler 10 will end up calling our iterator here. That's okay. This should probably be a public function anyway. Okay, so we will say let mute p. That's what. Here, so I've got behind this terminal. I've got Wikipedia. list of consecutive integers. Good. Let p equal 2. So yeah, they start with that. But also, we know that 0 and 1 are not primes. I'm going to say, and this needs to be mutable, of course, maybe prime at 0 equal false, and at 1 equals false. Now we're going to say let mut p equals 2. We'll say while p times p is less than or equal to n. So you start at, once you get past p squared, this, you don't have to keep checking this. The issue is that any value that p divides that is less than, how does Wikipedia put it? It's sufficient to mark the numbers in step 3, starting from p squared, as all the smaller multiples of p will have already been marked at that point. This means the algorithm is allowed to terminate in step 4 when p squared is greater than n. Essentially, if a number is if you're checking for divisors and you check up to the square root of a number, then you don't have to keep checking. Because if you were going to find another number less than n but greater than its square root, then you would have already found and divided by that number, which would have been less than its square root. So you can stop checking at p squared. So while p squared is less than n, we'll say we need to now mark all the multiples of p that are starting at p plus 1. So let's say if let's, so what we want to find is we want to find the, oh no, we need to do a for loop. So we need to say for I in, let's say, p squared through, or up to n, step by p. Skip the first one. We don't want to mark p itself as false. So we're going to mark these as not prime, as not maybe prime, because we know that they're composite. We will say maybe prime at I equals false. Cool. And then p plus equals 1. Now what we need to do is we need to skip to the next thing that we know is not composite. So we'll say maybe prime at starting at p, which is now 1 past our previous p, dot position. So this will be an if let some pos a position of b, and position I think is going to pass as a reference. So we just want to find the next truthy thing, the next one that we don't know to be non-prime yet. If let some pos equal that, then p also needs to be advanced by that offset from wherever it was to the next true. So that p is now the index of the next maybe prime value, which we can conclude now is prime, or else it would have been crossed off as a multiple of one of the composites by this point. Method not found in bool. Oh. No, of course it's not. There, good. Maybe prime. Okay, so let's check this out. So we have our test primes, and we believe that's right. Oh, by the way, this technique is called trial division, apparently. What we were doing before. So we might keep it around just for test purposes. But for now, I'll use that to test prime sieve. But if we end up, when we end up replacing the guts of that iterator to use sieves, we may keep a trial division implementation around just for testing. So test prime sieve. This will be, let's see. Let's take the first. Oh yeah, so this is fine. So these are primes. What we need is let mut, let's say, is prime. we'll have a grid of what we know to be prime. Vec. So equals vec. We want the first, let's say 1,000. 1,000 is not too slow. N equal 1,000. All right, it takes the value first. Start this one off. Initialize all to false, and we'll say for p in primes new dot take while same thing as above there. P is less than n, right? But now we don't have to collect it. Say is prime at p as u size, because primes returns u64s, equals true, because we know those are true. Good, so now we just need to assert equal prime sieve, then should be giving us the same thing as that is prime, right? Expected u size found u64. Right. Let's make this, should be a u size. I set it a u size. Oh, because of this right here. Less than, so let's make this p as u size, less than n. There. Interpreted as generic arguments, not interpreted as comparison. Wasn't that interesting? P as u size. Whoa. So, we seem to have a bug. Oh, you know why? Because we're setting... Oh, why is that? Why is that? So the left side there, prime save is returning false, false. This should be 0, 1, 2, 3, 4, because it thinks that 4 is prime. There's your problem. So let's just set n to something much smaller for now while we debug. Why is the right side so much? Oh, because this is still out. This should have been n to begin with. Good. False, false, true, true. Yeah. So we have a bug. Oh, yeah. Okay. So if we didn't find another prime here, that means there aren't any more. So we can say else break. But that doesn't fix the bug. So we'll say for I in p squared, step by p, 10. Oh, we do not want to skip 1 because we're starting at p squared. I thought we needed to start, yeah, no, we're doing a p plus 1 there. There we go. That fixes that. So now let's make this 1,000. Cool. All right, so now we have a prime sieve. Okay. Implement, say, add prime sieve function. Yes, push. No, I don't want to open a pull request. So now, in order to make Euler 10 work, all right, we need all the primes below 2 million. Oh, actually, that's fine. Yeah, that will work. That'll work just fine. So we might want to replace that iterator anyway for performance at some point. But for now, we do not need to. Cool. If we needed the first 2 million primes, that would be different. So now this becomes, instead of primes, let's import the prime sieve. This will be some primes below. And so we'll make a prime sieve. And as u size. Right. That's interesting. Okay, prime sieve and as u size dot filter. bools that are true. Dot count, right? It's dot counter dot len in Rust. Okay, let's make this instead of dash dash lib. Dash bin Euler 10. Filter. Web bool is not an iterator. Of course it's not. Don't be silly. In fact, this can just be into iter. U64 because of return type. Oh, we want the sum, not the count. Anyway. Filter. Oh, this is going to add up a bunch of bools. What am I thinking? I need the indexes. So what I need is dot map. No, dot filter map, right? First has this. So we're going to take a and we need the indexes. So dot enumerate dot filter map. The index, the bool. So if the bool is true, then sum is the method I know, which is very cool. This was recently added to Rust as I write this. Then sum I dot sum. All right, sum usize is not implemented. Oh right, this thing wants a U64. So instead of just I as U64. What does I mean? Oh, ignored probably. Right, so let's unignore this. Let's see how fast this is now. Okay, too fast. So now there's no reason to ignore this. Just to verify that this thing fails, if I change it. Yep. Outstanding. Let's just time it if cargo build dash dash release. Time target release. Euler 10. Well, how do you like that? Much faster. Cool. Let's get rid of the little micro benchmarking code. Instant now. We don't need that. We just need that. Dash release dash dash bin. 10 and cool. Yep. You know what this can all be? I don't usually like squashing commits. I don't think this is worth the branch. Amend, commit all. Use prime sieve function in Euler 10 for performance. Use prime sieve prime function for Euler 10 performance. I take it back. It was worth it. Reset head. Oops. Log and get reset. This one. Yeah. So okay. So we'll go ahead and make the use prime sieve function in Euler 10 for performance. Sieve Euler 10 for performance. Yeah. Now we can say we know it's a function from the previous commit. Cool. Oh, whoops. Am I on main? Yeah, okay. So the branch didn't end up getting used anyway. That was kind of all over the place. All right. Your branch is ahead of main. Push. Done. Be back soon.